Happy day all. So today's session is about the introduction for deadlock and the prevention mechanisms. So to begin with, let's see what a deadlock is, what are the possible conditions for a deadlock to occur, and how to handle the deadlock, followed by the deadlock prevention mechanisms. So the definition of a deadlock is, a deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource held by some other process. So before we could deep dive into the definition of a deadlock, let's consider an example for better understanding. So in this example, consider a one direction road and we have two cars, car 1 and car 2, which is approaching each other simultaneously. Okay. So it's very obvious that neither the car 1 nor the car 2 will be able to move forward. So this particular situation or scenario, we call it as a deadlock situation because there is no progress. Neither the car 1 nor the car 2 will be able to move forward. So a similar situation arises in our system as well. So here the road is going to be the resource and the car 1 and car 2 is going to be the two different processes. So let's consider the definition of a deadlock again. In terms of a diagram, we have two resources, resource 1 and resource 2. The process 1 is holding the resource 1 while requesting for the resource 2, which in turn is been held by the process 2. And the process 2 is requesting for the resource which is held by the process 1. So it's very clear that neither the process 1 nor the process 2 will be able to execute because it needs the resource which has been held by the other processes. So this is what we call it as a deadlock situation in system. So there are four different conditions for a deadlock to occur. The condition number 1 is mutual exclusion. Second is hold and wait, no preemption followed by circular wait. So when all these four conditions are going to be true, then we can say that the system has entered into a deadlock situation. So let's see what it is one by one. The first one is mutual exclusion. So here, when two or more resources are in a non-shareable mode, then we call it as a mutual exclusion. Meaning, only one particular process can use one particular resource at one point of time. The resource cannot be shared between multiple processes. The second condition is called as hold and wait. So under hold and wait condition, the process should hold one particular resource while it has been waiting for the another resource held by some other process. So in the previous diagram, if you see, the process 1 is holding the resource R1 while it is waiting for the resource R2. So this is what we call it as a hold and wait condition. The third condition is no preemption. So preemption means when we forcefully remove a resource from the process is called as a preemption. But here we are not supposed to forcefully remove any resources from a process. So the process will acquire the resource, complete its task and eventually release the resource by itself. So there is no forceful release of a resource. So if this particular condition holds, then the system is likely to get into a deadlock situation. The last condition is called as a circular wait. So here if you see a set of processes waiting for each other in a circular fashion. So if you consider this diagram, the process P1 is requesting the resource R2 which is held by the process P2. The process P2 is requesting a resource R3 which has been held by the process P3. And the process P3 is requesting for the resource R1 which in turn is held by the process P1. So the process and the resources here are placed in a sequence of a loop. So if the processes and resources are going to be in this particular sequence, then we can say that the circular wait condition is satisfied. So if all these conditions are going to be true, then we can say that the system is likely to get into a deadlock state. So there are various ways in which a deadlock can be handled in an efficient way. Deadlock prevention, deadlock avoidance, deadlock detection and deadlock recovery are the ways in which the deadlock can be handled efficiently. Well, each and every mechanism has its own pros and cons and limitations as well. So let's look into the deadlock prevention mechanism in brief. The deadlock prevention techniques refers to violating any one of the 4 necessary conditions. By violating or eliminating any one of the 4 conditions, we can say that prevent the system from entering into a deadlock state. So let's see the various approaches in which we can violate the conditions. So we've discussed earlier that the resources should be in a non-shareable mode, only then the deadlock situation can occur. So by making the resources as a shareable one, we can violate that particular condition. So again, there is a limitation here. We cannot make all the resources as a shareable one. Like say for example, printer is one of the resource where we cannot make it as a shareable one. Thus, the shared resources do not cause deadlock, but there are some resources that can be shared among the processes leading to a deadlock situation. So the next prevention mechanism is by violating the hold and wait condition. So there are 2 different approaches in which the hold and wait condition can be violated. So the first approach is by eliminating the wait condition. The process specifies the resources it requires in advance, does not have to wait for allocation after execution starts. Like say for example, we have a process P1 and it requires 2 resources for its execution, say for example scanner and printer. Now let us assume the process is going to execute for 30 minutes. For the first 15 minutes, it's going to use the scanner, and for the next 15 minutes, it's going to use the printer resource, right? So what the process P1 will do, it will request for both the resources, scanner and printer, during the initial stage itself. So if both the scanner and printer are available at that point of time, then it will be allocated to the process P1. And hence the process P1 will start executing its task. For the first 15 minutes, it will use the scanner, and for the next 15 minutes, it's going to use the printer. Now, this way, it does not need to wait for any other resource which has been held by any other process, because in advance, it will request and acquire all the resource which is required for a task completion. But there is one disadvantage in this approach where the scanner and printer is being idle for 15 minutes. Say for example, the first half the printer is going to be idle, and for the next half the scanner is going to be idle. So this is not an efficient way of utilizing the resources of a system. And the second approach is the process might not know which particular resources it will need in future. Like say for example, it might assume that it needs a scanner and request for a scanner, get the scanner resource and start its operation. But in future, it might require any other resource type as well. So at that particular point of time, what happens is it will request for the resource printer, but it has to release the scanner resource while waiting for some other resource type. So that we call it as eliminating the hold condition, where the process has to release all the resources it is currently holding while making a request for a new type of resource. So thereby, by eliminating either the wait or the hold, we can say that the system may not enter into a deadlock situation. So the third prevention mechanism is by eliminating the no preemption condition. So the no preemption condition states that we are not supposed to forcefully remove the resources from the processes. The process will make a request for a resource, acquire that, use the resource, and then release by itself in a natural way. So let's see the first example. So let's see this example where a process has resources R1, R2 and R3, and it is waiting for the resource R4. So here, if a process has resources R1, R2 and R3 and it is waiting for the resource R4, then it has to release all the before it could make a new request for another resource type. And the second approach is we have 3 different processes, P1, P2 and P3. The resource which is required for the process P1 is been held by the process P2, and P2 resource is been held by the process P3. But the P3 process is executing its operation. So where P1 and P2 are in a waiting state, it is waiting for the resource being held by some other process. So we can preempt the resource which is held by the process P2 and give it to the process P1 for its execution. So the second approach is we have three different processes, process P1, P2 and P3. Process P1 and P2 are in a waiting state while P3 is executing its task, because the process P1 is waiting for the resource held by P2 and the process P2 is waiting for the resource held by P3. The P3 process is in a running state, right? So what we can do is we can preempt all the resources held by the process P2 and give it to the process P1 for its execution. So this way we can avoid the deadlock situation using the no preemption condition. So the last prevention mechanism is called as a circular wait. So under circular wait, we've seen that if the process and resource are going to be in a loop sequence, then we can say that the system has entered into a deadlock situation. So by just breaking the loop, we can say that we can prevent the system from entering into a deadlock state. So the problem of a cyclic wait can be solved by assigning a priority number to each resources. So how can we accomplish this approach is by giving a numeric value to each resources. Say for example, we have resources R1, R2, R3 and processes P1, P2 and P3. Let us assume the numbers given to the resources as 1, 2 and 3, right? So P3 cannot request for resource R1 or R2 because it was previously holding the resource R3. So the next request which it can make is for the resource R4. So it has to follow the strictly increasing or the strictly decreasing order. So the next request for the resource must be greater than the previous request for resource to remove the circular wait. Right? So say if in this particular scenario, the P3 can request only for the resource greater than R3. So it cannot request for the resource which is lesser than the value. So here the value is 3, here the value of the resource is 1. So it cannot request the resource lesser than the resource which it was holding previously. It should strictly follow the increasing or the decreasing order. A process must first release all Ri such that I is greater than or equal to j. Now say for example, the process P3 needs R1 for its execution, then what it has to do is release this particular resource and then it can acquire the resource which is lesser to it. Like say for example, it needs the resource R1, then it has to release all the values greater than the R1. Meaning it has to release this R3 connection, it has to disconnect this particular edge, only then it will be allocated with the resource R1. So thereby we can break the loop between the R3 and P3. So the greatest limitation of this particular approach is determining the relative ordering of different resources. So by just violating or eliminating the 4 necessary conditions, we can prevent a system from entering into a deadlock state. Thank you.